Hi, here we will discuss about the project exploring the state-of-art algorithms for brain tumor classifications using MRI data. Here, this paper reviews and compares the latest algorithms used for classifying brain tumor from MRI images. It covers the traditional machine learning methods and recent deep learning models, including CNN and ResNet and vision transformations. The author discussed how these models are trained on popular public datasets like a browse and explained these steps of image pre-processing, segmentation, feature extractions and classification. For this paper we are taken for the reference and this one is taken by current 2025 paper. Okay, from the June month, 16th June 2025 paper we have taken, and the reference papers we have used for this model. Okay, so what the proposed approach of this model means? For the proposed approach, this paper presents an efficient FPGA based system for automatic brain tumor detections from MRI images using a 3x3 convolutions edge detections method with a stride 1 convolution. The proposed architecture is developed as a soft IP core in Verilog HDL and synthesized on Xilinx Zynq 7000 FPGA platform. This system applied a customized 3x3 convolution kernel over each MRI with a stride 1, ensuring that every pixel is proposed and fine images detailed or preserved for accurate tumor detections. So each detection results are used to segment and highlight abnormal regions, and thresholding mechanisms is employed to differentiate between a normal and abnormal images. Hardware resource utilization, including a lookup table, flip-flops and power consumptions, is analyzed after synthesis to verify system efficiency. The experimental results confirms that the proposed FPGA implementations provides a real-time processing and reliable brain tumor detections without low power usages, making it suitable for portable and embedded medical devices. The stride 1 approach has guaranteed maximum detections accuracy and detailed edge preserving in all test cases. Now we can verify the paper. This paper is purely designed for the brain tumor detections from brain MRI. Okay, so in the state-of-art paper, it will be covered the segmentation, pre-processing and feature extractions and classification method. But in the proposed architectures, it will be totally reduced. It will be come with a very less logic sizes using a proposed architecture. Okay, so that architectures it will be present with the figure 2, the block diagram of proposed methodology for MRI image processing. Okay, so initially it will be loaded with the input MRI images. After that it will be converting the images into the grayscale, okay, and read the data and stored into the registers for 3x3 stride 1 convolutions, and after that we need to read the data using a Verilog HDLs, and we need to check the data. It's a how many number of white pixels available in that binary images. Okay, after that we need to go with the normal abnormal predictions, okay, and then we go with the final output display. Okay, so that is the process of this work, and additionally the stride 1 convolution is a very important architecture of this work. Okay, so here the figure 3 it will be showing the convolution technique step by step. Okay, so here they are used for 8x8 image pixel for reference. Okay, and they'll be checked with the 3x3. Okay, so here this is a tile size. Okay, so P1 to P9. Okay, so that is a 3x3, and it will be moving with a stride 1 method. That means a 1 column. Okay, so first step 1 it will be taken from the 0th column. Step 2 means it's a start with the first column, and step 3 means it start with the second column. Okay, so as per that it moving step by step, we need to cover complete image pixels. Okay, so here for this project we have used 256x256 image resolution. For this 256x256 image resolutions, how many tiles we can use with the support of 3x3 means we can calculate easily 256 divided by 3. Okay, that means 85 for rows. Okay, 85 into 85.3. okay, so 7278 tiles we need to use for this 256x256 image resolution. Okay, so after that we will be get the Sobel edge detection. Okay, and that Sobel edge detections we have used for the brain tumor detection. Here you can verify the figure 4, the system architecture for edge detections. Here we are using for 2 row counters and FIFO generator and shift register for splitting the 3x3 convolutions there. Okay, so after this convolution process, we need to add the value and we need to compare the value, and finally we taken as the Sobel data, okay, edge detections data. Okay, and then we process this architecture. So this is a proposed flow chart for normal and abnormal tumor based brain detections. Okay, so here also same. Okay, so we are loading the input images, MRI convolutions. After that we need to process the edge detections and detect the number of zeros and ones. Okay, and after that the number of ones we need to calculate it. Okay, that is a PER calculator. Okay, and after that we need to put a threshold. Okay, how many number of ones we are used for this images. As per that number of threshold, we predict that is a normal MRI or abnormal MRI. Okay, so that is the concept of this work. This work we have designed in Verilog HDL code and synthesized in Xilinx Zynq FPGA, and we compared all the parameters of LUT, flip-flops, and power consumptions. Okay, so now we can verify the Verilog HDL coding part. This is the Verilog HDL coding we have designed for this brain tumor detections. Okay, so here we have used for Sobel edge detections and calculated PER and tumor detections method, and this work we have synthesized and simulated using for modelisms and Xilinx BAD. Okay, so first of all, for this approach, now we need to use the image processing to convert into the binary form. Okay, so for that we need to use this image GUI. Okay, so here we can choose any images. Okay, so we have chooses the MRI data sets. Okay, so here we have chooses a total number of images for abnormal and normal predictions. Okay, so if we choose any images, it will be convert the data into the hexadecimal form. After that we use that hexadecimal value in the coding architectures. Okay, and then we process the simulation model. Okay, so here this is the simulations we have start with a do sim.do method. Okay, so once the simulation done, we can possible to analyze the waveforms. Okay, and then we can verify the output images, that is a normal or abnormal predictions. Okay, now it will be taken time for 4 milliseconds for execution time. Okay, so now it's showing for it's a normal MRI brain images. Okay, and we have chose the two output, normal and abnormal. Okay, so if it is normal high means it will be showing for normal brain MRI, otherwise it will be showing for abnormal MRI. Okay, so now we can check this MRI data, okay, in a binary form using this output image form. Okay, so here you can verify it. So this one is a normal output. Okay, so if we load the browse images, we can choose any abnormal activity. Okay, example this one I can choose means. Okay, so now we can run the same procedure do sim.do, so we can verify that output. Okay, so this is an output for the tumor detections MRI. Okay, so here you can verify the abnormal bit, it will be goes for high. Okay, and now we can check this binary images. Okay, so this is a binary images for abnormal brain tumor detections. Okay, and then we have synthesized this code in Vado. Okay, so here you can verify the code, the brain tumor detections of Sobel detection. Okay, so here you can verify the post implementations, how much LUTs it will be take means 442, and flip flops it will be take for 518, and BRAM it will be take 1.50, and IO it will be take 55, and PUBG 1. Okay, so power occupied, the static power equal to 0.105 and dynamic power equal to 0.008. Okay, so here we can verify this in a RTL schematic. So this is a RTL schematic for this architecture. So initially we loaded the image data into the Sobel edge detection. Instead of the Sobel edge detections, it's having a line buffer to convert the data into the 3x3 method. After that we use for image convolutions, we need to split that 3x3 to 9 pixels. Okay, after that we process this Sobel hardware machine, that is this reference paper we have used. Okay, so this one is a Sobel hardware machine architecture. Okay, and this is a hardware machine internal architecture of RTL. Okay, and after that we go with the D flip-flop for number of sampling and averaging the data, and also we do with the image recording. Okay, and finally we taken the process of the pixel value. That pixel value we can calculate with number of ones. Okay, so that is a Sobel data we are taken here. Okay, and calculate the PER. Okay, so this is a PER calculations model. Okay, so once it will be calculated, that PER data we given to the tumor directions. Okay, so it will be predict the data with support of the threshold background. Okay, and then it will be chooses the abnormal activity and normal activity. Okay, and finally we taken as a normal and abnormal output data. Okay, so this is a flow of this work with the support of RTL. Okay, so and then we have written abstract document for this project. Okay, so here you can verify the title, abstract, introductions, and existing method of paragraph. Okay, and proposed method, and advantages, disadvantages, and related notes for this project. Okay, so everything for project support we are given. Finally we come with the literature survey and references. Okay, thank you.